Welcome everybody to the lecture for Chapter 7, Probability, Living with the Odds. Section C, the Law of Large Numbers. Basically, what the Law of Large Numbers says is that there's a numeric probability of something happening, like when you flip a coin. There's a 50-50 chance that you're going to get heads half the time and tails half the time. But in reality, like those of us in the 120E lab class learned recently, in real life, it doesn't always turn out to be exactly that way. In reality, you sometimes get, like this in this experiment here, with rolling a die, lots of different results besides what the numbers tell you should get. See, by the numbers, your true chance for each number on a six-sided die, you have a 1 in 6 chance. And when you divide that, it comes out to be about 167, which is this blue line right here. So you see that they got all kinds of percentages besides 0.167 until they hit about 500 times rolling the die. Then after that point, they started to get closer and closer to that line. And then when they got really big, about 4,000 rolls, they started getting to where they were very close to the 1 out of 6. The more times they rolled it, the closer they got to the expected 1 out of 6, the blue line. And that's how the law of large numbers works. The more experiments you run, the closer to the true probability you get. Here's another example. A roulette wheel has 38 numbers, 18 black and 18 red, and the numbers 0 and 00 in green. Assume that all possible outcomes, the 38 numbers, have equal probability. What is the probability of getting a red number on any spin? Well, like before, we have to create a fraction with our total number of tries on the bottom. In this case, how many total opportunities do we have? The total number of outcomes is 38. That's how many numbers there are. And the total number of ways a red number can occur is 18, and that's what we put on top. So we divide that, and we get this fraction that you saw just a second ago. So we have 18 over 38. And if you practice doing this on your calculator, you'll get what they have here, 0.474. So that's how you figure out the probability. You take the total number of outcomes, you put that in your bottom, in the denominator, and the number of ways that what you're trying to figure out can occur goes in the top, and then you divide. So let's look at a practical question. If people in a casino spin the wheel 100,000 times, the same roulette wheel that we were talking about a minute ago, about how many times will a red number be the outcome? The law of large numbers tells us, as it's played more times, the proportion of times that it shows a red number will get closer and closer to 0.474. So if we multiply that by the total number of tries, which is 100,000, we should get 47,400 times. If you want to try that, you just multiply 0.474 times 100,000. And you should get this, and that equals about 47.4% of 100,000. That's what you're finding whenever you multiply that together. All right, good job. Let's move on to another concept called expected value. So again, we're working with events that have a certain probability of happening attached to them and a certain value attached to them. So suppose event 1 has a certain value and a certain probability, and event 2 has a certain value and a certain probability. You can add these together to get an expected value, and this can be extended to a large number of events. Okay, what in the world does that mean? Well, let's look at an example. Suppose an automobile insurance company sells an insurance policy with an annual premium of $200. Based on data from past claims, the company has calculated the following probabilities. An average of 1 in 50 policyholders will file a claim of $2,000. An average of 1 in 20 policyholders will file a claim of $1,000. And an average of 1 in 10 policyholders will file a claim of $500. Assuming that the policyholder could file any of the claims above, what is the expected value to the company for each policy sold? Okay, so how do we approach this? Well, there is a positive number to work with. That's the premium cost. Now we're looking at this from the insurance company's perspective here, because they want to know the total value of the insurance policy. So the positive number is what is paid to them for the premium. So $200 is a positive number for them. And then the negative numbers are the claims. So we consider each of these numbers to be a negative. And then the probability of this $200 is 1, because that's a sure thing. You're going to buy a policy. If not, none of this matters, because you're not going to file a claim if you don't have a policy. So if we then look at each of these claims, we have to look at the probability for each one. So if it's a 1 in 50 chance, that means you're going to have a fraction. So the way that it said to do it was the value. So we already decided that this needs to be a negative number. So it's going to be a negative 2,000 times its probability. So this is 1 in 50. So that's how the value for that first one is going to be written. It's going to have this negative number times the probability. So the next one would be negative 1,000 times 1 over 20. And then this last one would be negative 500 times 1 over 10. And of course this beginning part was positive 200 times 1. Our policy, our premium probability was 1. So now we just have to add all of those together. So let's look at what that would look like. Here is that equation all spelled out for you. And you can actually put this straight into your calculator. You don't even have to put these parentheses, as long as you use the negative sign, not the minus sign on your calculator. The negative sign is towards the bottom, right next to the enter. And you would just put in 200 plus, and then the negative sign, 2,000 times 1 divided by 50 plus the negative sign, 1,000 times 1 divide 20 plus negative sign, 500 times 1 divide 10 equals. And if you did exactly that, you should get 60. And if you did not get exactly that, then look back at what you did. Make sure that you're using the negative sign and not the minus sign. And make sure that you're doing the divided sign right here in between the 1 and the 50, and you're using times, not X. Okay. So what this suggests is that once you go through all of that, this means that the company can expect the return per policy to be about $60. Interesting, huh? Okay, so let's switch gears again. They've thrown a couple of different topics into this section. So now we're going to talk about something called the gambler's fallacy. It's the mistaken belief that because you've had a streak of bad luck, you're due for a streak of good luck. It's basically what keeps addictive gamblers in the game. And you should know that there's absolutely nothing to back it up, so it's definitely not something you should ever depend on being true, that if you're having a bad streak, that you're due for a good streak. So let's say that you are playing the coin toss game, in which you win $1 for heads and you lose $1 for tails. After 100 tosses, you are $10 down because you got 45 heads and 55 tails. Well, you don't want to quit, so you keep playing. You play until you've tossed 1,000 times. Now you've gotten 480 heads and 520 tails. Does the result agree with the law of large numbers? Have you gained back any of your losses? Pause the video for a minute and think about that. Think about what we learned about the law of large numbers. Have you gotten closer to what the numbers tell you you're supposed to get? Have you gotten closer to the 50-50 that you should get for a coin toss? Okay, so the proportion of heads in your first 100 tosses was 45%. After 1,000, you increase your proportion to 48% by getting 480. So this does agree with the law of large numbers because it's closer to 50%, but you're still behind. Your losses have actually increased from $10 to $40, even though you got closer to 50% proportionally. Moral of the story, get out while you're ahead, or just don't gamble to begin with. Okay. Let's talk about streaks for a moment. The problem with streaks is that they're coincidental. Tossing a coin has just as much a chance of getting this result, heads, tails, tails, heads, tails, heads, as getting a whole bunch of heads all in a row. That is because you have a 50-50 shot every single time. These results are equally likely as each other. You can fool yourself into thinking you're getting a hot streak when actually you've just stumbled into a coincidental run. Think about it this way. How much sense would it make for a farmer to use that same logic? He knows at this time of year his likelihood of getting rain is about 0.5 or 50%. It hasn't rained in 10 days, and he needs to decide whether to start irrigating. Is he justified in postponing irrigation because he's due for a rainy day? You could think of the 10-day dry spell like a losing streak, but is it really logical for him to depend on that? Okay, so gambling houses usually have their games set up so that their games have a probability of winning a higher percentage of times than the players do. They call this the house edge. It's the expected value to the house of each individual bet. As they say, the house always wins. Okay, that was it for today. Thanks for listening. I will see you next time.